Out in the endless silent dark, far beyond the rocky worlds and the great belt of asteroids, a gas giant reigns. Saturn, the ringed jewel of our solar system, holds court over a family of more than 80 moons. Most are cold, dead worlds of rock and ice, silently pirouetting through the void for eternity. But one of them is different. One of them is keeping a secret. From a distance, it appears unremarkable. A tiny bright sphere, no wider than the length of England. It is named Enceladus, a giant from Greek myth, imprisoned beneath a mountain. The name is more fitting than its ancient authors could ever know, for this moon is also a prisoner, locked beneath a shell of ice, and deep inside that frozen prison, something is stirring. Something is calling out across the silent gulf of space. For decades, we saw it as just another point of light, another celestial body catalogued and filed away. The Voyager probes, in their grand tour of the 1980s, gave us our first fleeting, tantalizing glimpses. They revealed a surface brighter than freshly fallen snow, the most reflective body in the entire solar system. They saw a landscape that was shockingly young, smooth and unblemished by the billions of years of cosmic impacts. Something was resurfacing this world, erasing its history. But the images were too blurry, the flyby too brief. The mystery of Enceladus would have to wait. It waited for a generation. It waited for a new kind of explorer. Not a human, but a machine of breathtaking complexity, an emissary of our curiosity sent on a one-way 7-year journey. Its name was Cassini. For 13 years, this magnificent automaton orbited Saturn, transforming our understanding of this planetary system. It gazed at the rings, danced with the Titan moon Titan, and repeatedly returned to the enigma of little Enceladus. In 2005, Cassini's sensitive instruments turned towards the moon's south pole. What it witnessed would rewrite the rules for where to find life. Erupting from the moon's surface like ghostly fingers reaching for space were colossal plumes of water vapour and ice particles. Geysers, hundreds of kilometres high, blasting material from within the moon at supersonic speeds, feeding Saturn's own E-ring. This tiny, frozen world was not dead. It was breathtakingly alive. The mythical giant was breathing. The source of these eruptions appeared to be long, parallel fissures in the ice, formations the science team nicknamed tiger stripes. These weren't random cracks. They were a sign of geological activity, of heat and energy radiating from the moon's interior. The implications were staggering. For a geyser of water to exist, there must be a source. A vast, subterranean reservoir of liquid water. A global ocean hidden beneath miles of solid ice. Suddenly the solar system felt like a much larger, more hopeful place. We had long searched for water, the fundamental solvent for life, believing it might be found on Mars, or perhaps Europa. But here, in an unexpected corner of the cosmos, was not just evidence of water, but an active world spraying the contents of its hidden ocean directly into space. It was an invitation, a sample, offered freely, a message in a bottle, cast into the cosmic sea. To understand the sheer wonder of this discovery, we must first grasp the conventional wisdom it overturned. For centuries, the search for life has been governed by a simple concept: the habitable zone, or the Goldilocks zone. This is the narrow orbital band around a star where temperatures are just right, not too hot, not too cold, for liquid water to exist on a planet's surface. Earth sits comfortably within our sun's habitable zone. Mars is on its outer edge, Venus on its inner. It was long assumed that life could only arise in these cosy, sun-warmed regions. Worlds in the outer solar system, like the moons of Jupiter and Saturn, were considered far too cold, frozen solid, and inhospitable. Enceladus shattered that paradigm. It demonstrated that a world doesn't need the warmth of a star to maintain liquid water. It can generate its own heat. This moon is engaged in a powerful gravitational dance with Saturn and with a neighbouring moon, Dione. As Enceladus orbits the gas giant, Saturn's immense gravity stretches and squeezes it, like a hand repeatedly clenching a rubber ball. This constant flexing, this tidal friction, generates enormous heat in the moon's rocky core. It is an engine of unimaginable power, running for billions of years, warming the world from the inside out. This internal heat is the key. It creates a remarkable environment at the boundary between the rocky core and the liquid water ocean above it. Imagine a place of absolute darkness, under pressure that would instantly crush any terrestrial submarine. Here, the heat from the core vents into the ocean floor, creating what we believe are hydrothermal vents. Think of them as deep-sea chimneys, superheating the surrounding water and infusing it with minerals and chemical compounds from the rock. On Earth, in the deepest, darkest trenches of our own oceans, similar hydrothermal vents are oases of life. Far from the sun's light, entire ecosystems thrive not on photosynthesis, but on chemosynthesis, harnessing chemical energy from the vents to survive. Creatures that seem alien even to us, giant tube worms, ghostly fish, armoured snails, flourish in this seemingly hostile environment. Could a similar chain of life exist in the sunless ocean of Enceladus? The evidence gathered by Cassini suggests it is profoundly possible. The probe did not just see water in the plumes, it flew directly through them. Its instruments tasted them. The analysis was a revelation. The plumes contained not just water and salt, but a rich cocktail of organic molecules: methane, carbon dioxide, ammonia, and complex hydrocarbons. These are the fundamental building blocks of life as we know it. Later, a final deep dive through the plumes before Cassini's mission ended detected something even more profound: molecular hydrogen. On Earth, molecular hydrogen is a delicacy for certain types of microbes. It is a potent source of chemical energy. Its presence strongly suggests active hydrothermal vents on Enceladus' seafloor, just like the ones that power life in Earth's abyssal plains. So, the recipe for life is there. We have the first ingredient, liquid water, and a lot of it. A global ocean containing more water than all of Earth's oceans combined. We have the second ingredient, the essential elements. The carbon, hydrogen, nitrogen, and oxygen found in the organic molecules, with phosphorus and sulfur almost certainly present in the rocky core. And we have the third crucial ingredient, a source of energy. The chemical energy produced by the hydrothermal vents, the very energy source that may have sparked the first life on our own planet. All the known requirements for life to begin and sustain itself appear to be present in this tiny, distant moon. The question is no longer, could life exist there? The question has become, how do we go and find out? And this is where the dream collides with a formidable reality. Reaching Enceladus is not merely a challenge. It is one of the most audacious and complex undertakings humanity could ever attempt. The distances involved are almost beyond human comprehension. Saturn is over 1 billion kilometers away. Even travelling at speeds of tens of thousands of kilometers per hour, the journey takes the better part of a decade. A signal travelling at the speed of light takes over an hour to travel from Earth to Enceladus and another hour to return. This is not remote control. It is sending a sophisticated, autonomous robot into the unknown and waiting for a postcard 2.5 hours later. The journey itself is just the first hurdle. The environment around Saturn is one of extreme radiation, a hazard that can fry the delicate electronics of any unprepared spacecraft. Then there is the issue of power. So far from the Sun, solar panels are virtually useless. Any mission to the outer solar system must carry its own source of power. This means a radioisotope thermoelectric generator, or RTG. These are essentially nuclear batteries, using the heat from the natural decay of plutonium-238 to generate a steady supply of electricity for decades. They are reliable and effective, but the plutonium they require is exceedingly rare, difficult to produce, and politically sensitive. Powering the dream of discovery requires a material we have spent decades trying to eliminate. Let's assume we overcome the journey, we build the perfect vessel, power it for the decade-long voyage, and place it in orbit around Enceladus. The next challenge is even more daunting. How do you search for life? The plumes offer the most direct path. A mission could orbit through the geysers, as Cassini did, but with instruments far more advanced and specifically designed to detect biosignatures. Imagine a flying laboratory, equipped with a suite of mass spectrometers capable of identifying complex organic molecules, lipids, or amino acids, the telltale signs of biological processes. It could search for specific patterns, for chains of molecules that are too complex, too ordered, to have been formed by random chemistry alone. It would be looking for a whisper of life in a blizzard of ice. But even this approach, while revolutionary, might not be enough. The plumes may only carry fragments of molecules broken down by their violent journey into space and exposure to radiation. To find definitive proof, to see life with our own robotic eyes, we must go to the source. We have to get through the ice. We have to touch the ocean. This is a technological leap as significant as the one that took us to the moon. The ice shell of Enceladus is estimated to be miles thick, and the surface temperature is a cryogenically cold -200 degrees Celsius. Landing a probe on this surface is hard enough. The terrain is unknown. The ice could be as soft as powder or as hard as rock. The plumes themselves, while a target for study, are also a hazard, creating a constant weather of falling ice crystals. Let's imagine our lander touches down safely near one of the tiger stripes. Now, the real mission begins. How do you drill through kilometers of ice in an environment where any normal mechanical drill would freeze solid? Engineers are exploring several radical concepts. One is a melt probe, a heated, torpedo-shaped device that would use its own RTG not just for power, but as a heat source to literally melt its way down through the ice shell. It would be a slow, painstaking descent, lasting months or even years, the probe inching its way downwards, analysing the ice layers as it goes, creating a frozen fossil record of the moon's history. Trailing behind it would be a fibre optic cable, its only link to the lander on the surface, which would relay its data back to Earth. The final moment would be one of unbearable tension. After its long journey through the solid ice, the probe would break through into the liquid abyss below. For the first time, a human-made object would enter an extraterrestrial ocean. What would it find? To explore this subglacial sea, the probe would need to transform, deploying autonomous underwater vehicles or cryobots. These would be our robotic scuba divers, swimming freely in the alien ocean. Picture a small, intelligent submersible navigating in total darkness, using sonar to map the seafloor and avoid obstacles. It would need powerful lights to pierce the gloom, revealing a landscape that has never been seen. Its primary objective would be to find a hydrothermal vent. It would follow chemical gradients in the water, sniffing out the telltale signatures of heat and minerals, homing in on the source of energy. The moment of discovery would be relayed across 1 billion kilometers of space. A camera, peering through a reinforced lens, would transmit images. First, just blackness. Then, perhaps, the faint glow of superheated water. The submersible's lights would illuminate a chimney of rock, billowing with dark, mineral-rich fluid. And then we would look for movement. We would not be looking for fish or squids or anything familiar. The life here, if it exists, would have evolved in a completely different context. It would be truly alien. Perhaps we would see microbial mats, thick carpets of single-celled organisms clinging to the rocks, drawing their energy from the vent's chemical soup. Maybe we'd find something more complex, something that has evolved to swim through the water, a simple multicellular organism. Whatever we found, its very existence would change everything. The scientific and philosophical implications of this discovery are profound. Finding life on Enceladus would not just be about finding alien microbes, it would be about discovering a second genesis. All life on Earth, from the smallest bacterium to the largest whale, shares a common ancestor. We are all one family, one tree of life. If the life on Enceladus has a different biochemistry, if its DNA or its cellular structure is fundamentally different from ours, it would mean that life is not a fluke. It would prove that the origin of life is not a unique, miraculous event that happened only once on our planet. It would mean that life is a natural, perhaps even common, outcome of chemistry and physics, given the right conditions. The universe would transform from a vast, sterile emptiness into a cosmic petri dish, teeming with potential. The challenges are not just technological, they are also profoundly ethical. This brings us to one of the most critical aspects of any such mission: planetary protection. We must ensure that our robotic explorers do not inadvertently contaminate the pristine ocean of Enceladus with life from Earth. A single terrestrial microbe hitching a ride on a lander could find the Enceladus ocean to be a paradise. With no natural predators and an abundance of nutrients, it could proliferate, potentially outcompeting or even destroying the native ecosystem before we ever have a chance to study it. It would be the single greatest act of biological vandalism in history. We would have travelled 1 billion kilometres, spent billions of dollars, all to find life, only to discover we had brought it with us. Therefore, any probe destined to touch the ocean of Enceladus must be sterilised to an unprecedented degree. This means baking its components at high temperatures for extended periods. It means bathing them in powerful chemicals and blasting them with radiation. The entire spacecraft must be assembled in the cleanest rooms on Earth by technicians in sterile suits to minimise any possible contamination. We must be absolutely certain that any life we discover is native to Enceladus and not an accidental tourist from our own world. The burden of proof is on us, and the stakes could not be higher. We have only one chance to get this right. So can we actually reach Enceladus and find life? The answer is a resounding but qualified yes. Yes, we have the foundational technology. We know how to build spacecraft that can travel to the outer solar system. We have the scientific instruments to detect the signs of life. We have the conceptual designs for landers, drills, and submersibles. But the commitment required is immense. A mission of this magnitude would be a multi-generational endeavour, costing billions of dollars and requiring the dedicated work of thousands of scientists and engineers for decades. It requires political will and a shared sense of purpose. It demands that we see beyond our immediate concerns and invest in a search for knowledge that may not yield its ultimate prize within our lifetimes. Proposed missions are already on the drawing board. Concepts like the Enceladus Orbolander or the Enceladus Life Finder outline detailed plans for how we might return to this captivating world. They map out trajectories, design instruments, and calculate risks. They are the blueprints for the next great age of exploration. The first step would be an orbiter, a successor to Cassini, that could fly through the plumes hundreds of times, building a high-resolution map of their chemistry and searching for complex biomarkers with unprecedented sensitivity. This would allow us to choose the most promising landing site, a location above an active vent that offers the best chance for discovery. Then would come the lander, the culmination of all our efforts. Its descent would be a moment of global anticipation. Its search for life, whether by analysing scooped-up ice from the surface or by deploying a probe into the depths, would be a scientific saga followed by billions. To find even a single alien cell would be the most profound discovery in the history of science, a moment that would forever divide human history into two eras, the time when we thought we were alone and the time when we knew we were not. It would force us to re-evaluate our place in the universe. It would raise new questions in biology, philosophy, and theology. If life can arise in a dark ocean so far from the sun, where else might it be hiding? On the scores of other icy moons in our own solar system? On the trillions of exoplanets and their moons orbiting other stars? The search for life on Enceladus is more than just a scientific quest. It is an expression of the deepest part of the human spirit. It is the same impulse that drove our ancestors out of Africa, that led navigators across uncharted oceans, and that lifted astronauts towards our own moon. It is the desire to know what lies over the next horizon. In the cold, distant plumes of Enceladus, we see a new horizon. We see a reflection of our own watery origins, a possible echo of the process that led to our own existence. We see a chance to answer one of the most fundamental questions we can ask. Are we alone? The journey will be long. The challenges are monumental. The outcome is uncertain, but the possibility, however remote, that we could stand on the brink of discovering a second genesis of life makes the endeavour not just worthwhile, but essential. Enceladus is waiting. Its secrets are being sprayed into space, a constant silent broadcast from a hidden, living world. It is an invitation, written in water and ice, across 1 billion kilometres of darkness. And sooner or later humanity will answer the call. We will go, we will search, we will find out. The quest continues. What if the signature of life, the very colour of a living world, is a shade we never thought to look for? For generations we have scanned the cosmic ocean with a profound and limiting assumption, a bias born of our own blue and green home. We searched for mirrors of Earth for pale blue dots orbiting distant suns, believing that the blueprint for biology was a universal constant, a single sacred text written in the familiar language of our own biochemistry. We gazed into the unfathomable darkness, listening for echoes of ourselves, all while the universe was patiently waiting to show us just how breathtakingly narrow our imagination had been. The story of our place among the stars is not one of finding a reflection, but of opening our eyes to a spectrum of possibilities so vast, so alien, that it forces us to redefine the very meaning of the word alive. Our cosmic neighbourhood, once thought to be a lonely island of stability, has in recent decades revealed itself to be an astonishingly crowded metropolis. The hunt for exoplanets, worlds beyond our solar system, has transformed from a fringe science, a dream whispered by philosophers, into a torrent of discovery. It began not with a triumphant shout, but with the faintest of tremors in the light of a distant star. We learned to watch for the most subtle of clues, the telltale gravitational wobble of a star being tugged by an unseen companion, a ponderous invisible waltz conducted across light years of empty space. This radial velocity method gave us our first glimpse into the galactic family, revealing worlds of unimaginable scale behemoths that dwarfed our own Jupiter, locked in orbit so perilously close to their stars that their years lasted mere days. These were the hot Jupiters, the first class of alien worlds to enter our catalogue celestial monsters that defied all our theories of planetary formation. They were not Earths. They were incinerated gas giants screaming through their parent star's corona, their atmospheres bleeding away into space like cosmic smoke. They were a declaration from the universe: your home is not the rule, it is the exception. Then came a new way of seeing, a technique of profound simplicity and power. We built patient sentinels telescopes like Kepler and pointed them at a single star-dusted patch of the Milky Way, instructing them to do nothing but stare. For years they watched unblinking, measuring the brightness of 100,000 stars with inhuman precision, waiting for the dip, the briefest, almost imperceptible dimming of a star's light, the shadow of a world passing in front of its face. This transit method was our gateway. The trickle of discoveries became a flood, a deluge of data that reshaped our understanding of the galaxy. Suddenly planets were not rare celestial jewels. They were common as the stars themselves. The cosmic census exploded. We found super-Earths, rocky worlds several times the mass of our own, their crushing gravity and thick atmospheres hinting at conditions we can barely simulate. We found mini-Neptune's planets with no analogue in our own solar system, caught in a mysterious state between rock and gas. We found planets orbiting two suns, their skies graced with twin sunsets, a reality torn from the pages of science fiction. We found rogue planets cast out from their stellar nurseries to wander the eternal night of interstellar space, lonely orphans of gravity. We built a cosmic bestiary, a catalogue of strange and often terrifying worlds. We found Kepler 78b, a planet of rock and iron so close to its star that its surface is a permanent ocean of molten lava, its very substance boiling under the stellar glare. We found planets where the pressure is so immense that the sky may rain diamonds. We discovered worlds wrapped in eternal darkness on one side, and scorched by perpetual daylight on the other, their atmospheres whipped into supersonic winds that circle the globe forever. Each discovery was a triumph, a testament to human ingenuity. But with each new world, a quiet desperation began to set in. In this sprawling, diverse zoo of planets, where were the gentle ones? Where were the worlds with stable orbits, with the right mass, with the gentle caress of liquid water? We refined our search, focusing on the habitable zone, that delicate sliver of space around a star not too hot and not too cold, where water, the solvent of life as we know it, could exist in liquid form. The Goldilocks zone. Even there ambiguity reigned. We found candidates, dozens of them rocky worlds of the right size in the right orbit. But they were phantoms defined only by their mass and their distance. We knew they existed, but we could not know them. Were they barren, airless rocks like Mars, Or were they Venus-like hothouses suffocated beneath a blanket of toxic clouds? To find out, we needed more than just a shadow. We needed to read the light itself. We needed a new eye on the universe, an instrument so powerful it could capture the faint glimmer of starlight passing through an alien atmosphere hundreds of light years away and decode its chemical secrets. With the launch of the James Webb Space Telescope, we finally had that eye. Its magnificent golden mirror, a honeycomb of cosmic perception, unfolded in the cold vacuum of space 1,000,000 miles from Earth. It was designed to look back to the dawn of time to see the first galaxies ignite. But it was also designed for something more intimate, to perform an act of interstellar forensics. As a planet transits its star, a tiny fraction of the starlight is filtered through its atmospheric fringe. In that filtered light, molecules leave their fingerprints, their unique absorption lines. Webb could read those lines. It could tell us if a world had water vapor, if it had methane, if it held the tantalizing chemical precursors to life. The telescope began its work staring into the hearts of distant solar systems, sipping starlight that had traveled for centuries to reach us. The data streamed back to Earth, a torrent of numbers and spectral graphs, each one a potential postcard from another world. And then it came, a signal from a star we'd studied before a red dwarf in the constellation Leo, just over 100 light-years away. A modest star cooler and dimmer than our Sun, but known to host at least one planet of interest, a super-Earth designated K2-18b, orbiting comfortably within its star's habitable zone. Previous observations had hinted at the presence of water vapor, a momentous discovery in its own right. But the data was inconclusive, shrouded in noise. Webb, however, saw it with crystalline clarity. The spectral fingerprint for water was there, deep and unambiguous. This world was wet. It had clouds, it had weather, it had the fundamental ingredient for a biosphere. The excitement in the scientific community was palpable. This was a world worthy of our deepest attention. But as the teams processed more data, as they refined the signal and stripped away the noise, something else began to emerge. It was a chemical signature they didn't expect, a molecule rarely found in such abundance. A gas that on Earth is produced almost exclusively by living organisms, dimethyl sulfide, the smell of the sea. The smell. On our planet, it is phytoplankton in the oceans that exhale this gas into the atmosphere. To find it on a distant exoplanet was a staggering, almost unbelievable proposition. It was a biosignature, a potential klaxon call from a living world. Yet even that discovery, as profound as it was about to be overshadowed. Because as the astronomers modelled the planet's atmosphere to account for these new chemical findings, a strange picture began to form. They tried to create a simulation that matched the data a computer model, that would show them what this world might actually look like. They ran the numbers again and again, convinced there was an error in their calculations. The models kept spitting out the same impossible result. The sky was not blue. It wasn't white or yellow or orange. Based on the way the unique atmospheric gases scattered the light of the local red dwarf star, the models insisted with the cold certainty of physics that the sky on K2-18b would be purple. A deep, vibrant, breathtaking violet, a sky the colour of amethyst stretching over an endless planet-spanning ocean. This was the moment the world stopped. This was the discovery that transcended the sterile language of scientific journals and ignited the global imagination. An ocean planet with purple skies. The image itself is poetry, a vision of sublime and alien beauty. But the implication is a revolution. A blue sky on Earth is the product of Rayleigh scattering the way our specific mix of nitrogen and oxygen scatters the shorter blue wavelengths of our sun's light more effectively than the red. It is a direct consequence of our atmosphere and our star. A purple sky tells a story of a completely different system. It speaks of an alien air, a different light, and perhaps a different kind of life. A life that evolved under the gentle ruddy glow of a red dwarf, a sun whose light peaks in the infrared. Perhaps the photosynthetic organisms in that vast ocean don't use chlorophyll, which absorbs red and blue light and reflects green. Perhaps they utilize a different pigment altogether, something like retinal, which absorbs green and yellow light and reflects red and violet, painting the biomass of an entire world in shades of purple and red. Suddenly, we are confronted with the awesome reality that our entire conception of a habitable world has been a planetary projection of our own image. We searched for a twin, but the universe has given us something infinitely more valuable a stranger. A world that forces us to tear up our old textbooks and start from first principles. This planet, this impossible gem, hanging in the darkness of Leo, is not just a new location on our celestial map. It is a fundamental challenge to our understanding of biology itself. It poses the central thesis of our journey, the question that will drive us forward into the unknown. If a world can have a global ocean, a temperate climate, and a sky of a colour we've only ever seen in sunsets and flowers, what other rules are waiting to be broken? What new forms could life take governed by a different set of environmental pressures, bathed in a different light, breathing a different air? This discovery is not an answer. It is an invitation to question everything we thought we knew about life in the cosmos, to shed our terrestrial biases, and to truly open our minds to the boundless, vibrant, and utterly alien possibilities that await us out there in the silent, star-strewn dark. We stand on the shore of a new cosmic ocean, and for the first time we have a destination that promises not the comfort of the familiar, but the thrill of the truly magnificently unknown. For centuries it was a crime punishable by fire, a heresy so profound it threatened to shatter the very firmament of our perceived reality. The idea that the pinpricks of light scattered across the velvet darkness were not divine lanterns or celestial decorations, but suns just like our own. Suns orbited by other worlds, other Earths teeming with possibilities we could scarcely imagine. This was the dream of Giordano Bruno, a dream for which he paid the ultimate price, a dream that whispered through the ages, refusing to be extinguished by dogma or the sheer crushing scale of the cosmos. For 400 years it remained just that, a philosophical ghost, a tantalizing speculation haunting the quiet halls of astronomy. We had no proof. The gulf between the stars was simply too vast, the light of any potential world too hopelessly lost in the blinding glare of its parent star. It was like trying to spot a single firefly dancing next to a colossal searchlight from 100 miles away. The challenge was not one of imagination, but of physics. The universe, it seemed, was content to keep its greatest secrets locked away. But human curiosity is a relentless engine. If we could not see these worlds directly, we reasoned perhaps we could see their effects. We could search not for the planet, but for its shadow, its ghost. The first breakthrough came not as a picture, but as a subtle rhythmic dance. We learned to watch the stars not just for their brightness, but for their movement, their infinitesimal wobble in the fabric of space-time. Imagine a dancer spinning gracefully, arms outstretched. If they were to suddenly grasp the hands of an invisible partner, their perfect spin would be thrown slightly off balance. They would begin to sway, to lurch, to orbit around a common centre of gravity that was no longer perfectly aligned with their own body. This is the essence of the radial velocity method. A lone star, when viewed from Earth, is a steady beacon, but a star with a planetary companion is a dancer with a secret partner. The planet's gravity, its constant silent pull, tugs on the star, forcing it into a tiny repeating pirouette. It's a wobble so minuscule that for a star many light years away, the movement is smaller than the crawl of a snail viewed from a mile up. To detect this celestial waltz, we had to build instruments of impossible precision spectrographs, capable of dissecting starlight with the finesse of a master surgeon. They measured the light's colour, looking for the most subtle shifts. As the star wobbled towards us, its light would be infinitesimally compressed, blue shifted. As it wobbled away, its light would be stretched, red shifted. A repeating pattern of blue, then red, then blue again was the telltale heartbeat of an unseen world. In 1995, this technique yielded its first spectacular prize, 51 Pegasi b. It was a revelation that was also a revolution. The first confirmed exoplanet around a sun-like star was nothing like the worlds in our own solar system. It was a gas giant larger than Jupiter, yet it whipped around its star in a blistering 4-day orbit, its atmosphere scorched to thousands of degrees. This hot Jupiter was a monster, a celestial impossibility according to the theories of the day. It was the universe's first great lesson to us: the budding planet hunters expect the unexpected. The cosmos was not built to conform to our limited experience. It was a place of breathtaking, beautiful strangeness. The discovery opened the floodgates, but the wobble method was biased. It was best at finding the giants, the massive planets orbiting close to their stars, the ones with enough gravitational muscle to make their suns dance. But what about the others? What about the smaller rocky worlds? What about an Earth? To find them, we needed a new way of looking. We needed to stare. We needed the patience of a saint and the unblinking eye of a machine. This was the philosophy behind the Kepler Space Telescope. Launched in 2009, its mission was one of profound simplicity and audacious ambition. Kepler would not scan the whole sky. It would fix its gaze upon a single small patch of the Milky Way, a field containing over 150,000 stars, and it would not blink for years. It was looking for the other kind of shadow, the most ephemeral of cosmic eclipses. It was looking for a transit. If a planet's orbit happened to be perfectly aligned with our line of sight, it would periodically pass directly in front of its star. From our vantage point light years away, this would cause a tiny, almost imperceptible dip in the star's brightness. The signal was minuscule. For an Earth-sized planet crossing a sun-like star, the dimming would be equivalent to watching a single gnat crawl across a car headlight from 10 miles away. Kepler's photometers had to be sensitive enough to detect this fleeting shadow, a dip of less than 1/100th of 1%, and it had to see it repeat with clockwork regularity to confirm it was a planet, not just a sunspot or some other stellar flicker. For 9 years it stared a silent sentinel in the dark, and what it sent back to us redrew our map of the galaxy. It revealed not dozens, not hundreds, but thousands of potential new worlds, gas giants, ice giants, super-Earths, mini-Neptunes, and rocky planets in orbits both serene and savage. Kepler transformed exoplanets from a fringe curiosity into a core pillar of modern astronomy. It took the question, are there other Earths? And replaced it with a statistical certainty. Based on its data, we now know that on average every star you see in the night sky is host to at least one planet. Our galaxy is not a barren desert with a few scattered oases. It is a teeming cosmic jungle thick with worlds. There are more planets than there are stars. Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS, took this hunt to the next level. Where Kepler stared at a small patch with deep intensity, TESS became a wide-eyed globetrotter scanning nearly the entire sky. Its mission was not just to count planets, but to find the best ones, the most interesting ones, orbiting the closest, brightest stars in our own cosmic neighbourhood. These nearby worlds were the prime candidates for the next great leap in our exploration. Because finding a planet is one thing, knowing it is entirely another. For that we needed an eye so powerful, so revolutionary, that it could see not just the shadow of a world, but the secrets hidden within that shadow. We needed the James Webb Space Telescope. A golden honeycomb of mirrors, a technical marvel a million miles from home, JWST was designed to capture the faint ancient light of the universe with unprecedented clarity. And one of its most profound capabilities is a technique called transmission spectroscopy. It is in essence the science of alien atmospheres. When a planet transits its star, a tiny sliver of starlight passes through the edge of its atmosphere on its way to us. And that atmosphere, thin and fragile as it may be, leaves its chemical fingerprint on the light. It acts like a cosmic prism, a filter. Molecules in the air, water vapor, methane carbon dioxide, each absorb very specific colors or wavelengths of light. When the starlight emerges on the other side, those colours are missing, leaving a pattern of dark lines in the spectrum like a barcode. By capturing this light and analysing this barcode, JWST can do what was once pure science fiction. It can tell us what an alien sky is made of. It can detect the building blocks of life from across unimaginable voids of space. This tool, this combination of the transit method and the unparalleled power of JWST, is what led us to a small, dim star unremarkable in every way, except for the family of worlds it secretly cradled in its gravity. It is a red dwarf catalogued as Kinthos 3, a star far smaller, cooler, and older than our own Sun. These crimson suns are the most common type of star in the Milky Way, long-lived and gentle, and for decades astronomers have considered them prime candidates in the search for habitable worlds. Tess first flagged a periodic dimming from Kinthos 3, a whisper of a transit that hinted at a world roughly 1.5 times the size of Earth. It was a promising candidate, a super-Earth, orbiting squarely within the star's habitable zone, that temperate band where temperatures are just right for liquid water to exist on a planet's surface. Ground-based telescopes were immediately called to action, using the old reliable radial velocity method. They watched the star wobble, and from that dance they calculated the planet's mass. The result was electrifying. The planet now named Kinthos 3b was not just a large rocky world. Its mass combined with its size gave it a density that was startlingly low. It was far too light to be a solid ball of rock and iron. The numbers pointed to only one plausible conclusion. A significant portion of the planet's mass had to be made up of something much lighter. Something like water, an immense globe-spanning ocean. The tantalizing possibility of a true water world, a world that might dwarf all of Earth's oceans, combined made Kinthos 3b one of the most compelling targets for the newly commissioned James Webb Space Telescope. The request was made, the time was granted, and the great golden eye turned its gaze toward the faint red star. It waited with inhuman patience for the precise moment that Kinthos 3b would begin its next transit. For a few precious hours, as the planet slid across the face of its sun, JWST's instruments drank in the filtered starlight. The data streamed back across 1 million miles of space to a team of anxious scientists on Earth. And when they processed it, when they translated the raw light into a spectrum, a collective hush fell over the room. The barcode was there, and it was breathtaking. The first and most prominent absorption line was unmistakable, a deep, sharp dip in the spectrum that screamed the presence of water vapour. Not just a trace amount, but a massive signature indicating an atmosphere absolutely saturated with H2O. It was confirmation of a water-rich world beyond their wildest hopes. The data suggested a dense, steamy atmosphere, a global water cycle on an epic scale. The dream of an ocean planet was suddenly vividly real. But as they looked closer, a puzzle emerged. There were other lines in the spectrum, other parts of the barcode they didn't immediately recognize. The models had predicted what a water-rich atmosphere around a red dwarf should look like. They expected water, carbon dioxide, perhaps some methane, and those were there. But there was something else, a broad absorption feature in the blue and green parts of the spectrum that was completely unexpected. The models couldn't explain it. This unknown chemical compound was greedily drinking the yellow, green and blue light from the star, while allowing the red and the violet light to pass through. For an observer on the surface of this world looking up the sky would be a bizarre and beautiful spectacle. With the primary red light of its star mixing with the deep violet light that managed to penetrate its strange atmosphere, the heavens of Kinthos 3b would blaze in a permanent otherworldly twilight. The sky would be purple. This single confounding detail changed everything. It elevated Kinthos 3b from an incredible discovery to a profound enigma. We had found our ocean world the holy grail of exoplanet hunting for half a century. We had proven that such places exist scattered among the stars, but in the same breath we had stumbled upon a form of atmospheric chemistry completely alien to our own experience. We had the evidence of a world, but no understanding of the forces that shaped it. The data points were like clues left at the scene of a cosmic mystery. We had the planet's size, its mass, its density. We had the chemical signature of its atmosphere, the ghost of its water, and the puzzle of its violet skies. Each piece of information was a breadcrumb leading us deeper into the unknown. Now the real work had to begin. The work of scientific sleuthing, of taking these disparate ghostly clues and assembling them into a coherent picture of a living, breathing world, a world of deep oceans and purple skies waiting for us across the dark. And so the vigil began. That first confirmed whisper from Kepler 186f's star system, the telltale dimming of its parent sun, had already sent an electric current through the global astronomical community. But that was just the prologue, the confirmation that our target was real, a world patiently orbiting its red dwarf star. The true story, the chapter that would redefine our search for life, was still locked away, encoded in the faint photons that had travelled for 500 years to reach our mirrors. Now the real work started, a painstaking process of teasing apart that ancient light, forcing it to confess the secrets of the atmosphere it had passed through. The world's most powerful telescopes, colossal eyes of glass and steel, swiveled in unison, dedicating their precious time to this one distant point of light, listening for the spectral echo of a world we could never touch, but were desperate to know. In the clean rooms and control centres scattered across continents and time zones, a hushed anticipation settled. This is the unseen heart of discovery, not a single blinding flash of insight, but a slow, methodical accumulation of evidence. For weeks, the data streamed in a torrent of numbers representing the faintest shifts in starlight. Each packet of information was a single brushstroke in a portrait that was still too vast and too abstract to comprehend. The first objective was to confirm the fundamentals, to lay the groundwork upon which all other theories would be built. The teams were hunting for the spectral signature of water, the unambiguous barcode of H2O printed onto the star's light. A planet in the habitable zone is merely a suggestion of life's potential. A planet with water is an invitation. You could feel the collective tension in the air, the weight of expectation pressing down on every analyst staring at their screen running diagnostic after diagnostic. Then it appeared, faint but unmistakable, deep within the infrared spectrum where the light is invisible to our eyes but crystal clear to the instruments of the James Webb Space Telescope were the absorption bands. They were like missing notes in a perfect chord, specific frequencies of light that had been swallowed by water vapor molecules in the planet's upper atmosphere. A quiet cheer rippled through the control rooms. It was a muted celebration, the kind reserved for professionals who know this is just the first step on a very long journey. But it was a profound moment nonetheless. They had found it. A vast planetary-scale ocean, or at least the overwhelming atmospheric evidence for one, existed 500 light-years from home. The model suggested not just clouds, but a deep, stable hydrological cycle. This wasn't a barren Mars with hints of ancient seas, nor a Venus with its water long ago boiled away. This was a true water world, a shimmering blue marble we assumed in the galactic wilderness. But science rarely delivers such a neat and tidy package. As the teams refined the signal, integrating days and then weeks of observations to filter out the cosmic noise, a strange dissonance began to emerge from the data. The water signature was there, robust and undeniable, yet something was interfering with it. The models, the elegant and reliable algorithms that had successfully predicted the atmospheres of dozens of other exoplanets started to break down. They predicted a certain profile of light absorption, a clean, predictable curve. The reality, however, was messy. It was like listening to a beautiful symphony with a persistent, unidentifiable hum in the background. At first, it was dismissed as instrumental error, a calibration issue, or perhaps interference from the planet's host star, a notoriously tempestuous red dwarf. They ran the data again and again, and they checked every circuit, every line of code, every assumption built into their atmospheric models. They collaborated with rival teams sharing their raw, unvarnished data, in a rare act of unified purpose, asking one simple question. Are you seeing this too? The answers that came back from Germany to Chile to Hawaii were all the same. The anomaly was real. It was not a ghost in the machine, it was a ghost in the planet's sky. There was something else in that atmosphere, something present in vast quantities, that was absorbing and scattering starlight in a way we had never seen before. The clean signature of a water world was being distorted, warped by an unknown chemical accomplice. The quiet excitement of the initial discovery began to curdle into a more profound, more thrilling emotion, deep, tantalizing confusion. This is where true discovery lives, not in the confirmation of what we expect, but in the glaring, persistent mystery of what we don't. The scientists were now cosmic detectives, and the spectrum of light was their crime scene. Every dip and spike in the graph was a clue, a chemical fingerprint left behind by the atmosphere's constituents. They began by peeling back the layers of known chemistry. They found nitrogen a stable and expected component for a rocky world of this size. They found traces of carbon dioxide essential for any potential biosphere. But the ratios were all wrong, skewed by the pervasive dominant signal of the unknown compound. The water was there, but its spectral voice was being shouted down by this other much louder presence. The easy assumption of a familiar blue marble began to evaporate, replaced by the unsettling possibility of something truly alien. The hunt was on for the identity of this mysterious molecule. The teams worked backwards using the precise frequencies of light that were going missing to predict the kind of molecular structure that could be responsible. Was it methane? The absorption lines didn't match. Sulfur dioxide. The signature was completely wrong. Every common atmospheric gas was proposed and systematically ruled out. The process was a slow, frustrating grind, a meticulous act of elimination. You have to imagine the scene: brilliant minds surrounded by whiteboards covered in complex equations staring at a single, jagged line on a computer screen. That line was a message from another world, and for months they could not decipher the language it was written in. The planet was actively resisting our understanding, guarding its deepest secret. It was a team based at the Max Planck Institute that had the first breakthrough. They started to think outside the box, exploring not just common inorganic gases, but more complex organic compounds, and even metallic elements that are typically found only in the crusts of planets not suspended in their skies. They theorized that perhaps intense volcanism on the planet's surface was spewing a unique cocktail of elements into the air, an aerosolized layer of fine, crystalline dust. This hypothesis led them down a new path. They began modeling how light would scatter, not just through gases, but through suspended particles, each with a unique refractive index. They were no longer just looking for what was absorbing light, but for what was physically bouncing it around, redirecting it, and colouring it in the process. Their models began to focus on a particular region of the spectrum on the border between blue and violet light. Here the anomalous signal was strongest. The unknown agent in this planet's atmosphere was exceptionally good at scattering shorter wavelengths of light. Our own sky is blue because nitrogen and oxygen molecules are the right size to scatter blue light more effectively than red light, a phenomenon known as Rayleigh scattering. It's a clean, predictable process. But the scattering they were witnessing from Kepler 186f was on another level entirely. It was far more efficient, and it was shifted even further down the spectrum. The models that best fit the data pointed to something astonishing. A high-altitude atmospheric layer saturated with a compound that didn't just scatter blue light, but was hyper-efficient at scattering indigo and violet light as well. The chemical candidate they landed on was almost unbelievable. It was a complex molecule involving alkali metals, specifically a form of vaporized potassium. While potassium is a common element, finding it in such a high concentration in a gaseous state, creating a planet-wide atmospheric haze was unheard of. Standard atmospheric models simply couldn't account for its stability or its source. Yet when they plugged the unique spectral properties of gaseous potassium into their simulations, the jagged, anomalous data curves suddenly snapped into focus. The persistent hum in the symphony resolved into a clear, resonant note. The chemical ghost had a name. It was a perfect, terrifying, beautiful match. The mystery of what was in the air was solved. But it immediately opened the door to a much larger, more profound question. What would a sky saturated with such a compound actually look like? For this, the scientists had to become artists, translating the cold, hard data of absorption lines into a visual reality. They built a simulation, a digital recreation of the alien sky. They programmed the specific light-scattering properties of the water vapour, the nitrogen, and now this newly identified potassium haze. They modelled the light from the parent star, a cool, reddish-orange K-class dwarf, and shined it through their virtual atmosphere. Everyone gathered around the monitors waiting for the rendering to complete. What they saw silenced the room. It wasn't blue. It wasn't even the pale orange or deep red one might expect under a dim red star. The simulation showed a world where the shorter wavelengths of starlight were scattered with incredible efficiency, but not in the way our sky does. On Earth, violet light is scattered even more than blue light, but our eyes are less sensitive to it and the sun doesn't produce as much of it, so our sky appears a crisp, definitive blue. Here the situation was entirely different. The red dwarf star emitted a different blend of light, and the atmosphere's unique chemical makeup didn't just scatter the blue, it aggressively scattered the indigo and the violet, blending them together. The result on the screen was a sky of breathtaking, impossible colour. The simulation depicted a deep, vibrant, almost electric violet. Near the horizon, where the light passed through more of the atmosphere, it would fade into a soft lilac haze, while the reddish sun would set not as a brilliant orange but as a muted, dusky rose disappearing into a sea of purple. The implications were staggering. We had been searching for a pale blue dot, a mirror of our own world, and had found instead a majestic amethyst orb. The data was telling us that if you were to stand on the shores of one of its vast oceans, you would not look up at a familiar azure canopy. You would be standing under a perpetual royal purple sky. The water of the oceans reflecting this alien light would not be blue but a deep, shimmering indigo, perhaps appearing almost black in its deepest trenches. The light filtering down to the ocean depths would be a dim, violet twilight, a world away from the bright sunlit waters of Earth's coral reefs. The very colour palette of this world was fundamentally alien. The artists and renderings, once speculative flights of fancy, were now being directly informed by rigorous verified data. The purple planet was real. This revelation sent a new wave of energy through the research teams. The initial confusion had transformed into a sense of profound wonder. Every scientist in the field had grown up with the foundational image of Earthrise from Apollo 8, that fragile blue marble hanging in the blackness. It was an icon that defined our place in the cosmos. But now we had found a world that broke that mold completely. It forced a fundamental re-evaluation of what a habitable planet could even look like. This wasn't just a new setting for life, it was a new context, a new set of rules. The very light that would power its potential ecosystems was a different colour. Photosynthesis, if it existed here, would have had to evolve to thrive on the light that made it through this violet filter light, predominantly from the redder end of the spectrum. The cautious excitement that had marked the discovery of water now gave way to a bolder, more thrilling sense of possibility. The teams began to understand that the anomaly in the data wasn't an error or an obstacle. It was the most important part of the discovery. It was the planet's unique signature, its declaration of independence from our Earth-centric expectations. They had set out to find a twin of Earth, and had, by a spectacular stroke of cosmic serendipity, found its far more exotic and mysterious cousin. The painstaking detective work, the sifting through terabytes of data, had paid off in a way no one could have anticipated. They had decoded the message in the starlight, and it described a world of impossible beauty, a world of deep water and purple skies. But even as they celebrated this monumental breakthrough, a new, more daunting set of questions began to form. This unique atmospheric chemistry, this pervasive potassium haze, wasn't just a matter of aesthetics. It would have profound implications for the planet's climate, its surface temperature, and its ability to shield potential life from the harsh flares of its red dwarf star. The purple sky was not just a beautiful backdrop, it was the central engine of a global system we were only just beginning to comprehend. The solution to one mystery had only served to unveil a dozen more, each one deeper and more complex than the last. We had learned the what, but now we had to confront the how and the why. How could such an atmosphere form, and how could it remain stable over geological timescales? And the most important question of all, the one that now hung in the air of every laboratory and observatory, was what could possibly be living and breathing beneath that strange violet ceiling. The search for answers would take us deeper still into the very heart of this alien world's mechanics, and challenge everything we thought we knew about the nature of life itself. The first reconnaissance was over, but the true exploration was just about to begin. For weeks the data had been a trickle, a maddeningly slow drip of photons collected from across 700 light-years of unforgiving void. Each packet of information, each faint tremor in the starlight passing through the atmosphere of Kepler 186f was a clue. But clues are not answers. They are whispers in the dark echoes of a possibility so profound it felt dangerous to even hope for. We had seen the hints of water vapour, yes, and that strange, inexplicable muting of light in the violet spectrum. But science demands more than hints. It demands a standard of proof so high, so unbreakable, that it can rewrite the story of existence. And for that we needed not a trickle, but a flood. The command was given a silent cascade of digital instructions that synchronized the most powerful eyes humanity has ever built. From the frigid, silent orbit of the James Webb Space Telescope to the high, arid plains of the Atacama Desert, our instruments turned in unison, staring into the constellation of Cygnus. They weren't just looking for a dip in starlight anymore. They were performing a cosmic interrogation. For 96 consecutive hours they stared unblinking as the world we had provisionally named Ethelgard completed 4 full rotations on its axis, a silent pirouette for an audience trillions of miles away. The floodgates opened. Terabytes of raw information poured down a river of numbers that held within it the character of a world. In laboratories across the globe the mood was not one of excitement, but of a sacred, terrifying tension. Every scientist knew what was at stake. The first breakthrough came not from what was there, but from its sheer, overwhelming abundance. The spectral signature for water wasn't just a timid dip in the graph. It was a vast, yawning chasm. The light from Ethelgard's star, a placid red dwarf, was being devoured by water molecules in quantities that defied all our planetary models save for one. The models for dry worlds, for worlds with scattered seas or icy shells, they all shattered against the weight of this new reality. The signal was so saturated, so profoundly deep, that it screamed of an atmosphere in constant dynamic equilibrium with a massive planetary-scale liquid reservoir. This was not the signature of clouds or atmospheric humidity alone. This was the exhalation of an ocean. It was the planet breathing its breath thick with the vapour of a world of water. But even that, as monumental as it was, could be argued. A peculiar, dense atmospheric composition, perhaps. An unknown chemical process mimicking the signal. The skeptics, the essential and vital voices of scientific rigour, still had room for doubt. The definitive proof, the single piece of evidence that would silence all debate, came from a different quality of light altogether. We were looking for a ghost in the machine, a flicker of light so subtle it had never been successfully detected from an exoplanet before. We were looking for its glint. When light from a star hits the smooth surface of a liquid, it reflects in a very particular way. It becomes polarized, its waves vibrating in a uniform direction like soldiers marching in perfect step. It's the same phenomenon that creates the glare on a lake at sunset, the reason polarized sunglasses can cut through the shimmer and let you see into the water below. For days, the team specializing in polarimetry saw nothing but noise. The faint signal was buried in the overwhelming unpolarized light from the star itself, a cosmic needle in a haystack of fire. They built algorithms designed to hunt for this specific orderly pattern, to listen for a single coherent note within a symphony of chaos. And then it appeared. As Ethelgard rotated, a specific region of the planet began to sweep across our line of sight. For a few precious hours during what would be the planet's mid-afternoon, the delta streams flickered. A tiny, almost imperceptible fraction of the planet's light suddenly snapped to attention. It was polarized. It was the glint. It was the unmistakable, unambiguous reflection of a distant sun in a liquid mirror. You are looking at that signal now. This elegant pulsing wave rising and falling with the planet's stately rotation. It is one of the most important discoveries in human history. It is the light of a star having travelled for 7 centuries bouncing off the surface of an alien sea, and then journeying for another 7 centuries to finally fall into the lens of our telescope. It is a handshake across time and space. There could be no other explanation. No solid surface, whether rock or ice, could produce such a perfectly coherent reflection. This was the death of doubt. Ethelgard was not a potential ocean world. It was an ocean world. A vast global liquid water ocean churning under the light of a star that was not our own. The dream we had chased for generations, the vision of pale blue dots scattered amongst the stars, had just found its first anchor in reality. We had found another shore in the cosmic ocean. The confirmation sent a shockwave through the community, but there was no time for celebration, because the second stranger mystery was deepening with every new data point. The enigma of the purple skies. Initial readings had suggested a haze, perhaps a chemical smog of tholins common in the outer solar system. Or maybe it was a simple trick of the light, an artifact of observing a planet around a dimmer, redder star. Our own sunsets are red after all. Perhaps a world orbiting a red dwarf would have its light scattered by the atmosphere in a way that produced a permanent violet-hued twilight. All the conventional explanations were logical, safe, and entirely wrong. The high-fidelity spectrum from Webb told a new, utterly bizarre story. The colour was not the result of simple scattering like the blue of Earth's sky. It was the result of absorption. Something in Ethelgard's atmosphere, or perhaps on the surface of its ocean, was actively and with incredible efficiency absorbing vast swathes of the yellow and green light from its star. It was filtering its sunlight, leaving only the red and deep blue ends of the spectrum to be reflected or scattered back into space. When you see red and blue light mixed together, your eye perceives it as purple, magenta, violet. This wasn't a sky. It was a filter, a planetary scale stained glass window. The question was no longer what colour the sky was, but what unimaginable process was so powerful that it could repaint an entire world. The answer began to emerge when two separate teams, one studying atmospheric chemistry and the other modelling ocean dynamics, decided to merge their data sets. This was the moment of genesis. They laid the water data on top of the light absorption data, and they saw it. The two phenomena were not just related, they were perfectly intricately correlated. The strongest water vapour signals indicating areas of higher surface evaporation and warmer ocean temperatures precisely matched the areas with the deepest, most intense purple absorption features. The ocean and the sky were telling the same story. The process responsible for the planet's strange colour was happening where the water was where the light was where the energy was. It was happening in the sunlit zone of the global ocean. And that is when the word whispered in hushed tones for months was finally spoken aloud in the official briefings: biology. This was not the signature of any known geology or chemistry. Minerals do not absorb light with such knife-edge precision. Chemical hazes are messy, smearing their absorption across wide bands of the spectrum. This was specific. It was efficient. It was the hallmark of a molecule that had been tuned, optimized, and perfected for a single specific purpose: to capture energy. It was the signature of a pigment. On Earth, the dominant pigment of life is chlorophyll, which absorbs red and blue light and reflects green. It is the reason our planet from a distance is a pale blue dot marbled with the verdant hues of forests and phytoplankton blooms. Chlorophyll is life's solution to capturing the energy of a yellow-white G-type star. But Ethelgard orbits a different star, a cooler, redder K-type dwarf. Its light peaks in the orange and red parts of the spectrum. For life to thrive there, it would need a different engine. It would need a pigment that could take advantage of the most abundant light available, one that would perhaps find the yellow and green parts of the spectrum less useful, and evolve to absorb them with ruthless efficiency, reflecting the rest. Reflecting blue and red, reflecting purple. Scientists on Earth didn't even have to invent such a molecule. It already exists here in the darkest, most extreme corners of our own world. In salt ponds and alkaline lakes where the conditions are too harsh for chlorophyll, you can find extremophile microbes, ancient archaea that use a different method. They use a purple pigment called retinal. It is the heart of a simpler, more ancient form of photosynthesis, one that might be far more common in the galaxy than our own green version. This is the paradigm shift. This is the turning point in our search for life. We are no longer looking at atmospheric anomalies or geological curiosities. The evidence forces us towards a conclusion that is as breathtaking as it is terrifyingly logical. The purple of Ethelgard is not a colour. It is a presence. We are likely witnessing the collective metabolic activity of a global biosphere, a living ocean teeming with trillions upon trillions of organisms that have painted their entire world in their own image. They are breathing water vapour into the air and using a purple pigment to harvest the light of their alien sun. The two great discoveries, the water and the colour, were never two discoveries at all. They are two sides of the same miraculous coin. They are the intertwined signatures of a living, breathing, photosynthesizing planet. The models were run again, this time with a new radical variable, a planet-spanning bloom of purple, retinal-based microbes. The simulation snapped into focus. The predicted spectrum matched the observed data with a precision that was chilling. The amount of light being absorbed, the sheer scale of the operation was staggering. To colour a whole world, the biological productivity would need to dwarf that of Earth's oceans. It implies a biosphere of incredible robustness and density, a living soup of planetary proportions. This isn't just life. This is life triumphant. Life as a geological force so powerful and widespread, it has defined the very appearance of its home. Within weeks, the consensus was reached. It moved like a slow, powerful tide through the global scientific community as independent teams in Germany, Japan, and the United States reran the numbers and with a mixture of awe and disbelief arrived at the same inescapable conclusion. The papers were published, the press conferences were called, but the true impact was felt in the silence that followed. The silence of a species that had spent its entire history looking up at the stars and asking the question, are we alone? For the first time we had an answer, and the answer was no. The universe was not a sterile, empty stage upon which we were the only actors. It was a cosmic garden, and we had just seen the first flower blooming in another part of it. Look again at the image of Ethelgard. It is no longer a mere point of light, a pixel in a digital frame. It is a destination. It is a world with continents we cannot see, with weather patterns we cannot predict, and with an ocean that holds the single greatest secret in the history of science. For 2 billion years, life on Earth evolved in isolation, a lonely experiment confined to a single crucible. We had only one example of biology, one tree of life, one way of being. We had no way of knowing if our way was the only way, if the rules that governed us were universal laws or merely a local bylaw. Ethelgard changes everything. It is our Rosetta Stone. It is data point 2. The existence of a second independent genesis of life is the most profound discovery we could ever have imagined. It shatters the idea that life is a fluke, a 1 in a trillion chemical accident. It suggests instead that life may be a fundamental property of the cosmos, that wherever you have liquid water, a stable energy source, and the right mix of chemical building blocks biology is not a possibility, but an inevitability. It implies that the silent starry sky above you is not an empty void, but a dark ocean teeming with unseen islands of biology. Worlds of green life, worlds of purple life, and perhaps worlds of colours and chemistries we cannot yet even conceive of. The silence of the universe has been broken not by a radio signal or a visiting spaceship, but by the subtle, persistent blush of colour on a world 700 light-years from home. We stand at a precipice looking down into a whole new chapter of existence. The questions that now confront us are immense, their implications echoing into the future of our species. What is this life like? Is it simple, single-celled, a planetary film of purple bacteria? Or have 2 billion years under a different sun led to complex multicellular creatures that swim in those violet seas? Does it have its own version of a Cambrian explosion? A riot of evolutionary creativity hidden from our view? And the most tantalizing, most dangerous question of all, does it think has this second genesis also, over the great sweep of cosmic time, led to consciousness? Is there something looking back? The discovery of Ethelgard has not ended our search. It has only just begun. We have found the shore of a new world. Now we must find a way to explore what lies beneath its purple waves. The silence that followed the revelation was not empty. It was a vacuum into which 1,000 questions rushed at once, a deafening roar of possibility and doubt that echoed in laboratories and observatories across the globe. For a breathtaking moment, we had stared into the face of the impossible, a world painted in colours previously reserved for dreams and fiction. The initial wave of pure, unadulterated awe, that feeling of a species turning a corner in its cosmic journey, began to recede. In its place, a colder, more formidable tide rolled in, the tide of scientific rigour. The celebration gave way to the interrogation. That single shimmering pixel of a distant world now resolved into a planetary disk of majestic purple and deep, endless blue was no longer just a discovery. It had become a challenge. It had become the ultimate intellectual crucible, a place where our most cherished assumptions about life would be tested by fire. The first and most ferocious battle line was drawn across the spectrum of that alien sky, the purple. It was beautiful, hypnotic, and profoundly troubling. To many it felt like a beacon, a colossal flare sent up by biology, screaming its existence across the void. The colour was so specific, so unlike the hazy red of Mars or the sulphuric yellow of Venus. It had the signature of something deliberate, a chemical manufactured for a purpose. Teams of astrobiologists began working backwards, reverse engineering a plausible ecosystem from a single dominant colour. They looked to the darkest corners of our own world for clues to the strange and ancient life forms that thrive where the sun is a distant memory. They found an echo in the halobacteria primitive archaea that flourish in intensely salty water. These single-celled organisms don't use chlorophyll, the green engine of most life on Earth. Instead, they use a different molecule, a protein called bacteriohodopsin, which contains retinal. This pigment absorbs green light and reflects red and blue, creating a vibrant, unmistakable purple. Could an entire planetary biosphere be based on this retinal world hypothesis? The idea was electrifying. It would mean the dominant life forms on this ocean planet might not be plants as we know them, but vast continent-sized mats of purple microbes. These organisms would be painting their entire atmosphere with the byproducts of their unique metabolism, creating a global biosignature so potent it could be seen from light years away. Imagine a world where photosynthesis, the fundamental process of capturing stellar energy, evolved down a completely different chemical pathway. The forests, if they existed, might not be green, but shades of deep magenta and violet. The very air filtered through this biological engine would carry a chemical fingerprint utterly alien to our own. The purple haze wouldn't just be a colour, it would be the planet's collective breath, a biological exhaust pipe venting into space. For those in this camp, the conclusion was as intoxicating as it was elegant. We were not looking at a strange geological quirk, we were looking at life. But for every scientist who saw a biological proclamation, another saw a chemical ghost, a grand illusion forged by non-living processes. Science, after all, is a discipline of doubt, and the burden of proof for an extraordinary claim rests squarely on the shoulders of those who make it. Skeptics pointed out that chemistry in its infinite complexity is more than capable of creating vibrant colours without any help from biology. The universe is a far stranger artist than we often give it credit for. Perhaps they argued the atmosphere is saturated with unique mineral aerosol, some exotic form of dust kicked up from the planet's crust, whose particles scatter light in just the right way to produce that amethyst veil. Certain compounds of sulfur, for instance, when subjected to intense ultraviolet radiation from a star, can form complex polymers with a distinct purple hue. We see hints of this in the enigmatic upper atmosphere of Jupiter. Another more unsettling possibility emerged from the study of the planet's star, a star slightly cooler and redder than our own Sun. Its light is intrinsically different. What if its specific stellar radiation, a unique cocktail of high-energy particles and photons, was interacting with a common mundane element in the upper atmosphere like nitrogen or methane? This interaction could be triggering a constant planet-wide aurora, a perpetual twilight glow, so pervasive that it dyes the entire sky. In this scenario, the purple is not a sign of life but a symptom of extreme physics, a celestial bruise caused by the constant battering of a volatile star. The world would be beautiful, yes, but also sterile and violent, its sky a false promise. The debate raged in online forums, in heated video conferences that spanned continents, and on whiteboards filled with frantic scrawls of spectral absorption lines and chemical equations. Every argument for a biosignature was met with a plausible, abiotic counter-argument. Every beautiful dream of a living world was haunted by the spectre of a dead one. This is the brutal, unforgiving nature of the scientific method. It demands that we first kill every other possibility before we can let hope live. We must prove it is not a ghost before we can declare it a god. And beneath that chromatic riddle of a sky lay an even deeper mystery, the ocean. The data was unambiguous. We were looking at a world swathed in liquid water, a planetary womb on a scale that dwarfs the Earth's own oceans. But the existence of liquid water is a paradox in itself. The planet orbits its star in the so-called habitable zone, that delicate cosmic shoreline where water shouldn't freeze or boil. Yet given the star's lower energy output, the planet should be a snowball, an ice world locked in a permanent deep freeze. For it to host a liquid ocean of this magnitude, something else must be at play. Something must be feeding an immense amount of energy into the system, creating a global thermostat that keeps the waters flowing. The search for this hidden furnace became an obsession for planetary geophysicists. One leading hypothesis centered on immense tidal forces. What if this water world is not alone? What if it's locked in a gravitational dance with a massive unseen companion, a gas giant lurking just out of view, or a hefty sister planet in a nearby orbit? This constant gravitational tug-of-war would stretch and squeeze the planet's very core, generating colossal amounts of frictional heat. The planet would be geologically hyperactive, its ocean floor riddled with hydrothermal vents pumping out heat and nutrient-rich minerals from the world's molten heart. The ocean wouldn't be warmed from above by a gentle sun, but cooked from below by the planet's own internal agony. This vision is both terrifying and tantalizing. It suggests an environment where life wouldn't begin in sunlit shallow ponds as Darwin imagined for Earth, but in the crushing absolute darkness of the deep sea, clustering around these oases of geothermal energy. Life's genesis would have been a creature of pressure and darkness, not light and air. Alternatively, the answer may lie in the very atmosphere that so confounds us. An incredibly dense atmosphere, perhaps 100 times thicker than Earth's, could act as a planetary pressure cooker trapping heat, with a runaway greenhouse effect that would make Venus look temperate. The air itself would be a thick, heavy blanket, allowing water to remain liquid even at temperatures that would normally see it freeze solid. But what would this atmosphere be made of? It would require a precise blend of gases, a cocktail so perfectly balanced that it warms the planet without boiling its oceans away. Discovering this chemical mixture is the next great challenge, a puzzle that our current telescopes can only begin to solve. Each of these possibilities, tidal heating, a super greenhouse effect, or some other unguessed-at mechanism, paints a picture of a world profoundly different from our own. It forces us to decouple our terrestrial assumptions. The conditions for life might not be a gentle miracle, but a violent, precarious balancing act on a planetary scale. With these environmental parameters in mind, the question of evolution becomes a journey into the deepest realms of speculative biology. If life exists there, it has been shaped by forces we're only just beginning to imagine. What sort of senses would evolve in a world bathed in perpetual purple light vision, if it developed at all, would be tuned to a completely different part of the spectrum? An animal from this world might be blind to the brilliant greens and yellows that dominate our own, but could perceive 1,000 subtle shades of violet and infrared that are invisible to us. Colours would have different meanings. What we see as uniform purple haze might to a native eye be a rich tapestry of information about weather altitude and atmospheric chemistry. Communication might not rely on visual cues, but on bioluminescence. In the deep dark waters of that global ocean, the only light would be the light that life makes for itself. The abyss could be filled with silent, shimmering conversations, a light show symphony of creatures signaling hunting and mating in the eternal night. The sheer scale of the ocean and the crushing pressure of its depths would favour evolutionary pathways toward gigantism. Life might move at a different tempo, with slow, colossal creatures drifting through the abyssal plains living for millennia. Without continents to act as barriers, species might be truly global, a single interconnected ecosystem stretching from pole to pole. The very concept of intelligence might take a different form. Would a species born in a featureless three-dimensional ocean ever develop the need for advanced tool use, the very thing that spurred our own cognitive development? Perhaps intelligence there is not manipulative but purely contemplative. Or perhaps it is collective, a hive mind spread across a shoal of millions of individuals, or more radically, the ocean itself achieving a form of planetary consciousness, a sentient sea as theorized by the great science fiction authors. These are no longer just fanciful ideas. They are serious hypotheses being debated by scientists who now have a real-world test case. We are being forced to confront the staggering possibility that life and even intelligence might not look anything like us. It might not even be recognizable as life by our current definitions. And this brings us to the most difficult challenge of all, one that has nothing to do with spectroscopy or geophysics, but with the limitations of the human mind, the challenge of bias. For centuries, our search for extraterrestrial life has been a search for ourselves. We have looked for Earth-like planets orbiting sun-like stars for life, based on carbon and water-breathing oxygen under a familiar blue sky. We have held up a mirror to the cosmos and have been disappointed when we haven't seen our own reflection. This purple world shatters that mirror. It forces us to confront our own profound lack of imagination. Every debate, every theory, every argument about whether its colour is biological or geological is filtered through the lens of our own singular experience on this one planet. We are trying to understand an entirely new context for life, using a vocabulary and a rulebook written from a sample size of 1. The scientists wrestling with this data are acutely aware of this trap. They're caught in a constant struggle to think outside the box of their own biology. How do you design an experiment to look for a biosignature you can't even conceive of? How do you recognize life when it doesn't use DNA or when it's not even based on cells? This ocean world is more than a destination. It's a lesson in cosmic humility. It's teaching us that the universe is not obligated to conform to our expectations. The greatest barrier to understanding this world might not be the immense distance that separates us, but the conceptual gulf between what life is here and what life could be out there. We have found a new shore, but we have no maps. Every step forward is a step into the unknown, a process of unlearning what we thought we knew. The data streams in the debates intensify, and the sense of awe is now tempered with a profound sense of responsibility. We are no longer just asking if we are alone. We are now confronting the far more complex question, even if we find life, will we be able to recognize it? And as our telescopes continue their silent, patient vigil, we realize that observing this world is only the first infinitesimal step. To truly understand it, we cannot simply look. We have to learn how to see. For months, the data was a beautiful, infuriating paradox. The spectrum of Arathos was a wall of violet noise, a constant, unchanging hum that offered no purchase for the climbing anchors of our understanding. Our most powerful telescopes, our most sophisticated analytical tools all returned the same enigmatic answer, a world wrapped in a featureless shroud of purple. The models we built based on every known geological and atmospheric process all failed. They predicted browns and greys from silicate dust, perhaps the hazy orange of a Titan-like smog, but never this regal, impossible violet. The planet was a locked room, and we were standing outside listening to the sound of a heart beating within, unable to find the key. The scientific community, once alight with the fire of discovery, found itself settling into the cold ash of a profound mystery. Was this it? Would Arathos forever remain a tantalizing jewel admired from afar but fundamentally unknowable? The very tools that had found this world seemed inadequate to decipher it. We needed more than just a sharper image. We needed a new way to see. That new way of seeing came not from a larger lens, but from a more subtle and elegant form of interrogation. A team at the Atacama Large Millimeter Array, leveraging a technique known as spectropolarimetry, decided to ask the light from Arathos a different question. Instead of just asking, "What is your colour?" they asked, "What is your shape?" Light as it travels through space is a wave, and like any wave it can oscillate in different directions. When it reflects off a surface or passes through a medium that light can become polarized, its oscillations aligning in a preferred plane. Most astronomical sources produce light that is a chaotic jumble of polarizations. But if the light from Arathos's parent star was passing through its atmosphere and reflecting off something structured, something organized at a molecular level, it would carry a faint, almost imperceptible twist. A signature encoded in the very geometry of the light itself. It was a long shot, a search for a whisper in a cosmic hurricane. The observations took weeks, accumulating photons one by one, painstakingly filtering out the noise from the star, from our own atmosphere, from the interstellar medium itself. The resulting signal was so faint, so delicate, it was almost dismissed as an instrumental error, but it was there. Buried deep within the data, a consistent repeating pattern of circular polarization. The light from Arathos was twisted. It was a discovery that sent a shockwave through the exoplanet community, for this was no random geological signal. A chaotic cloud of dust or a uniform gas cannot produce such a signature. This specific type of polarization, this handedness, is the hallmark of molecules that are chiral. Molecules that exist in two mirror image forms, a left-hand and a right-hand version, just like your own hands. Non-biological chemistry, the kind that happens in interstellar clouds or volcanic vents, is indiscriminate. It produces a perfect 50-50 mixture of left and right-handed molecules, a racemic blend that cancels out any polarization signal. But life, at least life as we know it, is deeply prejudiced. On Earth, every amino acid that builds the proteins in your body is left-handed. Every sugar in your DNA is right-handed. This homochirality is one of the most fundamental and mysterious properties of life, a chemical fingerprint that biology leaves on its environment. And here, light years away, broadcast across the electromagnetic spectrum, was a signal of that same prejudice. The molecules responsible for the purple hue of Arathos were not a random chemical soup. They were overwhelmingly of one specific handedness. The planet wasn't just a painted rock, it was organised. It possessed a collective molecular-level architecture. The locked room door had not just been opened, it had been blown clean off its hinges. Suddenly the entire paradigm shifted. The question was no longer what mineral creates this colour, but what metabolic process requires such a molecule. The answer proposed in a flurry of theoretical papers was as elegant as it was revolutionary. It began not in the sky, but in the vast planet-girdling ocean below. On Earth, in our own primordial past, long before the evolution of complex chlorophyll-based photosynthesis, simple organisms like halobacteria developed a more rudimentary method of harnessing sunlight. They used a purple pigmented molecule called retinal, a close relative of the compound that allows your own eyes to see. This molecule acts as a simple proton pump. When struck by a photon of light, it changes shape, moving a proton across a membrane and creating an electrical gradient, a tiny biological battery charged directly by the sun. It's an incredibly efficient if simple way to make a living. It doesn't produce oxygen, it just produces energy, and its signature colour is a brilliant, shocking shade of purple, because it absorbs light most strongly in the green part of the spectrum, the very peak of a sun-like star's energy output while reflecting away the red and blue light. The new model that emerged was breathtaking in its scope. Arathos, they proposed, was not merely a water world, it was a retinal world. Its immense ocean, a continuous surface larger than all of Earth's continents and seas combined, was not a sterile basin of H2O. It was a living soup, a thick, thriving culture of microbial life forms, all built around this purple light-harvesting engine. They were the base of the entire planetary food chain, the foundation of a global ecosystem, running on a completely different operating system from our own. This wasn't a world with life on it. This was a world where the ocean was life. But this theory had to explain more than just the ocean. It had to account for the sky. How does a microbial sea paint the entire atmosphere violet? The answer lay in the planet's dynamic climate, which we had already observed but never fully understood. Arathos has no large land masses to disrupt its weather patterns. This creates staggering globe-spanning storms with winds that make our most powerful hurricanes look like gentle breezes. These hypercyclones churning the ocean surface for thousands of miles would create a constant, massive aerosol of seawater. But on Arathos, that aerosol would not be sterile saltwater. It would be a fine mist teeming with the purple retinal microbes. Lifted high into the stratosphere, these organisms would form a living haze, a biological shield suspended miles above the surface. From our distant vantage point, we were never looking at a gas. We were looking at a planet-spanning living cloud. A biosphere so pervasive, so deeply integrated with its planet, that it had become an inseparable part of its atmospheric chemistry. This single, powerful idea acted like a master key, unlocking every other puzzle Arathos had presented. It explained the chiral signature. The vast colonies of organisms would naturally produce a homochiral form of retinal. It explained the colour perfectly, an exact match for the light absorption profile of a retinal-based pigment under a G-type star. It even explained the bizarre thermal readings we had been struggling with. A living haze would absorb and re-radiate heat in a completely different way than a dust or gas cloud. It would create a unique thermal blanket, keeping the planet's surface warmer than it should be, and generating the strange layered temperature gradients that had perplexed climatologists. The planet wasn't just a static ball of rock and water, it was a self-regulating biological entity. A true Gaia, its climate and its life locked in a symbiotic dance on a scale we'd never dared to imagine. We began to run the models again, but this time we didn't input geology. We inputted biology. We programmed the simulators with the optical properties of retinal, the aerosolizing potential of a storm-racked ocean, the metabolic heat output of a trillion microscopic engines. And for the first time, the screen in front of us resolved into a familiar image, a perfect, deep, mesmerizing purple. The model was a mirror reflecting the reality of Arathos back at us. We were looking at the theoretical blueprint for a living world. We could model the great bloom's vast purple gyres swirling in the oceanic currents like cosmic ink. We could predict seasonal changes as the planet's tilt would alter the sun's angle, causing the retinal haze to thicken and thin, making the planet appear to breathe in and out over the course of its year. We could even begin to speculate on the rest of the ecosystem. What hunted these purple microbes? What sort of complex life could evolve in a world where the primary energy source was so different, where the very air was suffused with life itself? The possibilities were dizzying, stretching the boundaries of our own biological imagination. This was no longer a matter of simple observation. It was a convergence of evidence, a grand synthesis of astronomy, chemistry, biology, and climatology. Each piece of the puzzle, once isolated and confusing, now snapped into place, reinforcing the others. The ocean, the sky, the colour, the temperature, the very twist of the light, they all told the same story. There were no longer competing theories of note. There was only this one terrifyingly plausible, overwhelmingly beautiful explanation. We had not found a little green man. We had not received a radio signal or deciphered a message. But what we had found was perhaps even more profound. We had found the coherent planetary-scale signature of a working biosphere, the unmistakable hum of a world-sized biological machine operating on principles both deeply alien and hauntingly familiar. It was the collective chemical shout of a world teeming with life, a shout that had been travelling across the interstellar void for 42 years, waiting for a species curious enough to listen, not just to its sound, but to its shape. The consensus was no longer a question of if, but of how. How does such a system truly function? What other secrets does it hold? Arathos had ceased to be a mere candidate for extraterrestrial life. It had become the benchmark, the ground truth. A world that was now pulling on the collective consciousness of humanity, beckoning us to close the distance, to move beyond the telescope, to finally reach out and touch the shore of another living world. And so, the journey that began as a whisper in the starlight finds its harbour. We have travelled together across an almost unimaginable gulf of space and time, following a thread of evidence so faint it bordered on statistical noise. We started with nothing more than a recurring dimming of a distant unnamed star, a shadow play performed on a cosmic stage. You watched as spectral analysis turned that shadow into a substance-transforming abstract graphs and chemical absorption lines, into the tangible promise of an atmosphere of water vapour, of molecules that had no business being there unless something truly extraordinary was at play. We have walked the winding path from tentative hypothesis to quantifiable data, from the sterile environment of the laboratory to the boundless canvas of the imagination. Now that faint whisper has grown into a roar, a symphony of discovery that echoes not just through the halls of science, but through the very core of our human identity. The final portrait, pieced together from countless hours of observation and relentless computation, is no longer a blur of probabilities. It is a world. It is a destination. An alien shoreline awaits, bathed in the soft violet glow of a sky that has never known the colour blue lapped by the waves of an ocean that has never reflected a human face. This single breathtaking revelation has taken the elegant, carefully constructed architecture of planetary science and astrobiology and shaken it to its very foundations. For generations, our search for life was a search for ourselves, a quest for a mirror image of Earth orbiting a stable sun-like star. We drew a line in the cosmic sand, a temperate band we called the habitable zone, and declared that only within these narrow confines could the miracle of life take root. We were looking for a pale blue dot, for a familiar chemical signature, for a reassuring echo of our own existence. But this world, this shimmering violet pearl, has done more than just broaden that zone. It has erased the line entirely. It has demonstrated with breathtaking clarity that our definition of habitability was never a universal law, but merely a description of our own home. It was a projection of our own experience, a form of cosmic parochialism we didn't even recognize until it was shattered. The planet orbits a star we once dismissed a tempestuous red dwarf, prone to violent flares, an environment long considered too hostile, too chaotic for life to gain a foothold. Yet here it is. Life, it seems, does not merely find a way. It rewrites the rules of the game. It doesn't just adapt to the environment. It seizes the environment, tames its fury, and forges a new kind of stability, a new kind of normal that we could never have predicted. The profound violet hue of its atmosphere is perhaps the most eloquent testament to this new paradigm. It is a declaration of biological independence. On Earth, life is fundamentally green, a planetary blush, driven by the chlorophyll molecule's masterful absorption of red and blue light reflecting the green light we see all around us. This process became our biological blueprint, the assumed universal standard for harnessing a star's energy. We built our atmospheric detection models around this assumption, searching for the red edge, the telltale spectral signature of chlorophyll-based photosynthesis. We were listening for a familiar song in a single narrow bandwidth deaf to the rest of the cosmic orchestra. This world, however, sings in a completely different key. Its life has not embraced chlorophyll, but has instead evolved its own unique molecular machinery, a system based perhaps on retinal or a similar chromophore, a biological pigment that thrives on the specific light spectrum of its red dwarf star. It absorbs green and yellow light with ruthless efficiency, reflecting the unused blues and reds, which combine to paint its skies in shades of lavender and deep indigo. This is not a trivial cosmetic difference. It signifies an entirely separate, independent evolutionary path, a second genesis. It means the tree of life has more than one root, more than one trunk. It suggests that the solutions to life's fundamental challenges are as diverse and varied as the stars in the galaxy themselves. We now understand that searching for life is not about finding a copy of our own biology, but about opening our minds to a whole periodic table of possibilities, a symphony of chemistry we have only just begun to hear. This discovery has re-energized and redefined the entire field of astrobiology. It has transformed it from a discipline of hopeful theory into one of empirical reality. The conversations among scientists have shifted dramatically, moving from if to how and where next. The models of planetary formation are being furiously rewritten to account for a world so water-rich, orbiting so close to such a volatile star. Geologists and atmospheric physicists are collaborating in unprecedented ways, trying to understand the feedback loops that must exist on this world to maintain its equilibrium. How does its global ocean, likely far deeper and more saline than our own, interact with its dense alien atmosphere to regulate temperature? What kind of geological activity, what form of planetary heat engine is required to drive the nutrient cycles necessary for such a thriving biosphere, without a large moon to stabilize its axis or stir its tides? These are no longer abstract thought experiments. They are urgent, tangible questions about a specific known place. Every new data point, every subtle shift in its light curve provides another piece of a puzzle so grand it will occupy the careers of entire generations of researchers. It has given us a scientific anchor, a ground truth in the cosmic ocean that allows us to test our wildest theories and dream even bigger. We are no longer explorers wandering a dark and silent forest, hoping to stumble upon a clearing. We have found the clearing, and we can see the light of 1,000 other potential campfires flickering in the distance. The future, once a distant horizon of hopeful speculation, is now a landscape of defined and ambitious missions. The knowledge of this world's existence acts as a powerful gravitational pull on our technological aspirations, drawing our future toward it. In development are the next generation of space-based observatories, telescopes with mirrors not of meters but of tens of meters, segmented and folded into origami-like configurations that will blossom in the vacuum of space. These colossal eyes will not just confirm the presence of an atmosphere, they will dissect it with a precision that seems like science fiction today. They are being designed with this purple world as their primary target, their instruments specifically tuned to hunt for the complex organic molecules, the biosignatures that its unique biochemistry might produce. We will hunt for the specific waste products of its alien metabolism, for the seasonal ebb and flow of gases that could signal a planetary-scale respiration. We will seek to map its clouds to distinguish continents from its oceans by the subtle polarization of reflected starlight, and perhaps, just perhaps, to detect the faint rhythmic chemical pulses of a global ecosystem in action. Beyond these magnificent observatories, even more audacious plans are taking shape on digital drawing boards. We're contemplating fleets of laser-propelled nanosatellites, wafer-thin probes that could be accelerated to a fraction of the speed of light. Such a mission, a true starshot, would still take decades, even centuries, to cross the interstellar void. It is a project whose architects will not live to see its arrival, yet we plan it anyway. Because for the first time we have a definitive address. We have a postcard from a neighbour, and the desire to answer that call to send a messenger across the gulf is an impulse that lies deep within our species. We dream of probes that could one day enter that violet sky, that could taste the chemistry of its air and dip into its global ocean, sending back the first direct confirmation of life beyond Earth. This is the new imperative, the grand challenge that will define space exploration for the 21st century and beyond. We are no longer just looking up. We are planning the journey. We're charting the course from our own fragile blue shoreline to that distant alien coast. We are preparing in our own small, determined way to finally go and see for ourselves. And as we stand here on the cusp of this new epoch of discovery, we must finally turn our gaze inward. We must confront the profound philosophical weight of what we have found. For all of recorded history, we have defined ourselves by our uniqueness. We have told ourselves stories of divine creation, of being the sole inheritors of consciousness in a vast, empty and silent universe. This belief, this story of our solitude, has shaped our religions, our art, our conflicts and our sense of purpose. It has been both a comfort and a burden, a source of pride and a wellspring of existential dread. But that story, the central pillar of the human narrative for millennia, has now come to an end. The silence has been broken. We now know with the certainty of scientific observation that we are not a singular miracle. We are a part of a much larger, much stranger, and infinitely more wonderful cosmic tapestry. Life is not an anomaly confined to one world. It appears to be a fundamental expression of the cosmos, a persistent and creative force that can bloom in the most unexpected of gardens. This realization does not diminish us. It does not make our existence less precious. On the contrary, it elevates us. It means that our own struggles, our own triumphs, our own fleeting moments of love and understanding are echoes of a universal theme. It connects our small personal lives to the grand sweeping narrative of the universe itself. We are no longer the lonely protagonists of an empty stage. We are members of a cast so vast and diverse we cannot yet comprehend it. We have been like a person who has lived their entire life in a single room, believing it to be the whole of reality. Now a window has been thrown open, and for the first time we can feel the breeze from an outside world, hear the distant sounds of an unknown city, and see the unfamiliar colours of a foreign sky. The knowledge that we are not alone is not an endpoint. It is the ultimate beginning. It asks of us a new kind of maturity, a new perspective on our own place and our own responsibilities. The tribal conflicts and petty squabbles that have defined so much of our history seem impossibly small when measured against the sheer scale of this new reality. Perhaps this discovery is the cosmic intervention we have always been waiting for, a unifying truth powerful enough to compel us to see ourselves not as competing factions, but as a single family of earthlings, representatives of our own unique, beautiful and precious pale blue dot. We are living in the age of discovery, a moment that will be remembered for as long as our species endures. Future generations will look back on this time as the moment humanity's horizons expanded to encompass the stars. They will learn about the distant light signals, about the painstaking analysis, and about the final stunning revelation of a world with oceans of water and skies of purple. This knowledge is now a part of you, a part of our collective human heritage. The next time you gaze up into the fathomless depth of the night sky, you will not see an empty void sprinkled with cold, indifferent points of light. You will see a sea of possibilities. You will know that behind one of those faint twinkles lies a world of wonders, a place of alien chemistries and unimaginable vistas. You will know that the universe is not waiting to be conquered, but is waiting to be met. And you will understand that our greatest adventure, the search for who we are and why we're here, has only just begun. The journey outward is and has always been the journey home.